identifying atoms and atomic arrangement within a matter. Everything in the universe, from dusts to galaxies, is made of building blocks called atoms. And those atoms are grouped into a periodic table according to their properties. When we explore our world or even the outer space, we develop methodology and equipment. This development is basically a process of harnessing physical and chemical properties of materials. And those properties of materials are determined by what atoms are inside the materials and how those atoms were arranged. Let's take a close look at the space telescope called James Webb. Its marvelous and spectacular golden mirrors are made of beryllium with gold coating. Because beryllium has the properties of being super strong and light, and the atom arrangement of gold enhances the reflection of infrared light. So, for materials, it is very important to know their atom composition and the arrangement among atoms, because they are determinative for material properties. By fully taking advantage of material properties, humans could keep creating technological wonders. But how? How can we know what atoms and atomic arrangement are actually in there? To facilitate the explanation, let's take a look at crystals. You all know emeralds and diamonds. These precious stones are mineral crystals whose atoms are arranged in a periodic order. This arrangement is also found in metals and alloys. This means precious stones, as well as your metal kitchen utensils, even aluminum Coca-Cola cans, are basically crystals, because their atoms are arranged in a periodic order. Then, questions. How to know what distances and angles between neighboring atoms? And what atoms are actually in there? Let's take a teeny tiny piece of a Coca-Cola can, which is made of aluminum. And imagine we enlarge it until the atomic arrangement could be seen, just like this. Within this periodically repeated structure, you can soon spot the smallest repeating unit. That is to say, if we replicate the unit, stacking them from up to down, left to right, to all directions, we will get the same structure as shown. And this smallest repeating unit inside the crystal is called unit cell. The unit cell contains the key to our previous two questions. And the tiny piece of the Coca-Cola can contains sufficiently lots of unit cells. Now, let's put the tiny piece inside a powerful analytical equipment called transmission electron microscope, or TEM. The electron beam generated by the TEM is able to unveil the answers to our previous questions. The atoms inside crystals form various atomic planes. Those planes act like mirrors. If the Bragg's law is satisfied, the atomic mirrors will deflect incident electron beam emitted by the TEM. And if we put a CCD camera to capture those deflected electron beam, we get an image called diffractogram. Moreover, there are various sets of atomic mirrors which form various spots on the diffractogram. The spots on the diffractogram gives us information on distances and angles between neighboring atoms. Note that the distance between atomic planes are 0.1 nanometer. But this method magnified the 0.1 nanometer distance into several millimeter distance between spots on the diffractogram. This magnification means that even if you are standing on the moon and observing the Earth, with your naked eyes, you can see even cars moving in the street on the Earth, but you are observing from the moon. Then it comes to our final question. What atoms are actually in there? Let's take a look at the composition of an atom. Even if we do not know what atom we are currently looking at, the atoms have the same composition. A nucleus, which is positively charged, and a single or several electrons, which are negatively charged. The electrons orbit the nucleus, running in different shells, which are named K, L, M, N shells, etc. For simplicity, Let's just look at K and L shells. In specific conditions, the electron of the atom can get disappeared. For example, the transmission electron microscope generates electrons which have very high energy that could knock off the electron of the atom of our sample. In this case, an electron from K shell of the atom is knocked away. Then, the electron from the outer shell, L shell, will travel to K shell. Since electrons in L shell have higher energy than those in K shell, this travel emits energy in the form of X-ray. This specific X-ray is actually called characteristic X-ray. It identifies what atom it is. This method is called EDS, Energy Dispersive X-ray Spectroscopy. And let's take a look at the EDX spectrogram. We can see that different atoms give out specific characteristic X-ray. That's how the atoms are identified. So now, we understand how we could know what atoms and how they are arranged inside a material. It not only serves as the basic foundation for the study of matter, but also helps us make most use of the existing materials and resources to create technological wonders, to explore and unveil the unknowns from our world and universe, to extend human knowledge and transcend our limits for generations.